So I've had several questions on how do I figure out what my instrument error is through my calculations, or how do I propagate those figures, those significant figures through my calculation, and what does it mean versus my standard deviation? Okay, so I'm going to give you an example. So here we have some grams of material. This could be your precipitate or it could be something else, it doesn't matter. You'll see it has 4 decimal places, so it has the same precision as the balance in the laboratory we use. Okay, so this material has a molecular mass of, let's say, 456.2382. Great. Okay, so how many moles is that, right? So we will just simply do the math, right, of this divided by that. We'll lock it down. And so here we have the moles. Okay, so for our starting material here, right, we had 5 significant figures. Here we multiplied it by something that has 7 significant figures. So our answer here, this number of moles, of course, following the rules, will have 5 significant figures. But we're going to keep them all, right? So right now this one has 5. Our error is in the 5th significant figure. So what is our volume? Okay, well, our volume is 25.00. And so we're going to want to get a concentration. So we'll just divide the moles by the volume in order to get the concentration. Awesome. So we've done math between something that has 5 significant figures and a volume that has 4 significant figures. That means our concentration will have 4 significant figures, right? So this answer, of course, if we were to report out this final answer, would be 0.0001082, right? So that error from our machines, right, in this case, the volume is actually the dominating error, would be in this place, right? So it would be 0.0000001. Okay, awesome. So, as usual, we will then take the average of these. What did I do wrong? Oh yeah, well, it helps if you spell average correctly. And the standard deviation. Great. Okay, so remember, these would have 4 significant figures. So when we continue the math, this would be this plus this plus this, right? So we would have that decimal place would be conserved, right? So it would be 0.0000001, so 6 zeros and a 1. All right, we add them together and we wind up with this, which will have the same number of significant figures if we were to propagate the error from the machine. But this is the number we come up with a standard deviation. So we'd like to use this, but this is the machine and this is our standard deviation. And then the question is, which one do you use? Well, the answer is pretty easy. It's always you use the biggest. So I'm going to have large. Oh, I'm going to have to stop that function. Move it down so we can do an array. Equals large. So what is the biggest number between those two? Well, it happens to be this number. So this is the number we're going with. Now remember, this is the limit of the machine. So how does this compare? Well, right, we have We have 1, 2, 3, 4, 5, 6 zeros in the 5, and of course here, right, it's going to be a 6, so the rule is to report 1. So this would be bigger. So our error would be 1, 2, 3, 4, 5, 6, 6. And then we'd have the matching number here, 0.0001087. Of course, it rounds it, so I'll make the cell bigger. And so that's how we're propagating. That's why we look at this propagation of significant figures, because it tells us where the error from the instruments winds up. Okay, and then we can compare that to our standard deviation. Now, if this, let's say, was a magnitude smaller, we would wind up using this instead.